Hello, everyone. Here's Johannes Weikenmeier. Welcome to another round of our Closer Look Open Journal Club in Biomechanics. We're excited to host Dr. Jing Yan today from the University of Texas at Austin. The other co-hosts here on the call are Emma Lejeune, Matthew Bursey, Adrian Buganza-Tipole, and Manuel Rausch. Dr. Yang, who's talking today, did his PhD at Caltech and then worked as a postdoc in the University of Madison, Wisconsin, under the supervision of Christian Frank. He will be talking today about his research work on adaptive quadtree meshing techniques in digital image correlation. I hand over the microphone to you, and I'm excited to see what you have to share.
Yeah, thank you for having me here. So today I'm sharing our new paper in the new digital image correlation method, but to solve the complex geometry and discontinuities. So you can see my laser points here. So for the audience who are not familiar with the digital image correlation, so it's also called a DIC. It's a very popular experimental method nowadays to measure the deformation of the solid materials. So it's an experimental technique. So in the experiments, we have some loading on the specimen. And at the side, we have the high-speed camera. So during the loading, we can use the camera, we can take the images of the sample. And also on the surface of the sample, so usually we paint some random speckle patterns. So you can see there's some black background and some random white dots. So image sequence is the multiple frames. So you can see the first frame usually is the image, that's a reference image before the deformation. And then you have the multiple images during this sample under the loading. And then we apply some image tracking algorithm. So by comparing the deformed images with the first undeformed reference image, and we can measure the deformation field. And also with the deformation field, you can also measure the strain fields. So this entire technique is called the digital image correlation. So why it's important is because for the mechanics, we have the experimental mechanics, we have the theoretical mechanics, we have the computational mechanics, right? So the experimental mechanics, so now you can measure the displacement field, you can measure the strain fields, right? So if you also know the stress, right, you can use these experimental data points, you can validate the theoretical models, you can characterize unknown materials properties. You can detect some fracture or cracks. Also, you can discover some new physics of the novel materials, right? So it's very popular. And also nowadays, this full field deformation measurement, the digital image correlation, they can generate quite fruitful experimental data. So they can also be combined with the data-driven or machine learning-based computational mechanics. So to give you a brief introduction of how this method has been widely used nowadays, because it can be combined with the quite various other diagnostic techniques at very different length scales. So in the nanometer length scale, so you can combine the digital image correlation with the atomic force microscopy. So you can measure the deformation, the length scale is on the order of the nanometers. So in the micrometer, you can combine this digital image correlation with the optical microscopy. You can measure the cell mechanics deformations. You can measure the twinning or shear bands because the DIC, they give you the full field information. So even there is some strain localization, some shear bands, you can measure all this strain localization quantitatively. So it's also widely used for the real life application in the engineering fields. So here the aircraft. Because this method, basically, they use the image tracking algorithms. So you can also apply some very large size images. So you can use the satellite images. So here, the land scale is on the order of the kilometers. So you can track the earthquakes, right? You can monitor the glaciers. You can also measure the planets, other planets' deformations. So it's widely used nowadays across various land scales. And not only for the solid materials, so in fluid community, there's the similar method. It's called the particle image velocimetry. So now we apply some particles. Right? You can track those motion of the particles. You can also monitor and quantitatively measure the flow field in the fluid mechanics. So currently, so in the international world, we have the society called the International DIC Society. So if you are students, you want to know better of this new technique, you can also log on to this website. So there's a very nice guidebook to guide you, like lots of the good practice guides, right? How to apply this new technique. And also there are the multiple available commercial software and academic open source codes. Right? You can also apply these methods and implement all these with your experimental data sets. So these some like very quite helpful resources. Today I'm going to show you the even though DIC had developed over like 30 years and had already been widely used, there are still like significant challenges. So the first challenge is so for the complex geometry, it's still very hard to measure those deformations. So why? So let's see in the DIC, you have the reference image. So that's the before the deformation, right? And this image, you have some grayscale values. You have some random speckle patterns. And after the deformation, you have some deformed image, right? So there are also another image. You have some grayscale values. So if there's like no complex geometry, like everything is so like a great rectangular shape, right? You can track some local subsets, right? You can track the motion of each subset. So you can do this by optimizing the cross correlation function. So cross correlation function is the integral of the f times g. So if you write the y, that's the motion of each subset at some translation vector u. So if you plot this cross correlation function, so the location of this cross correlation function peak, so that's corresponding to the u. So that's the translation vector of each subset. So if everything is so nice geometry, right, there's no problem at all. You can solve this problem. But what if you have like a circular hole here, right? So if you still apply the conventional method, right? So for subsets, like they don't like cross this hole, that's okay. But if there's a subset, like it had the interaction with the hole, right? So you see the partial of this subset, you don't have the image grayscale value at all. So you can imagine you have less information. So this subset, you have some problems. So mathematically, you can also measure the measurement noise floor. So based on the like the measurement noise of in your experiments, and also the image grayscale value. That's a gradients of the image grayscale values. So for those subsets, like across these holes, right? You can imagine the gradient of the grayscale values. Like you lack some information here because for this subset, this like integral, you have smaller number than the other there's no hole areas, right? So which means this subset you have a larger error. So you can see the complex geometry, it will have the problem when you want to track the deformation accurately near these holes. But this problem is very important because in the real life, right, many of those like engineering application or academic application, you have sample like their shape or their geometry, they are not rectangular. So like a real aircraft, you have some windows, you have some doors, right? For some sample, you have some like a ring shape, right? So it happens, right? Excuse me. And also nowadays, the complex geometry, they can like be beneficial to improve the experimental efficiency. So for example, you can design an experimental sample with some carefully designed shape, right? So now you can still do the simple uniaxial tension experiment, but because the sample shape is quite complex, so some area the strain may be under the biaxial tension state, some area the strain they may be uniaxial tension, some area they may be shearing. So now you can see you have just one sample under one simple loading mode, but your results can be quite fruitful. You have lots of the data sets, but with just like a much fewer number for the testing. So this can make your experiments much more efficient. So this is the first challenge. So I want to say that, so you see like this complex geometry is very common and it's very demanding. So we want to improve how do we solve this complex geometry more accurately and also faster. So the second challenge is for the discontinuities. So imagine you have the subset, there's the crack here, right? So for the other areas, if there's no discontinuity, that's no problem at all. But if there's some like discontinuity, and if you have a subset that just across this discontinuity crack, right? So if you want to track the motion of this subset, you have problem because the part of this subset, it stays, and the other part of this subset, it goes up. So you may get something is the average value of this subset. That's you. So you will smear this discontinuity field. Or like if you use some iterative method for the tracking, like this subset may not converge. So for the discontinuity, it also has a problem, use the conventional method. And here's some example. This discontinuity is also very common problems because the fraction mechanics is a very popular topics, and lots of people they track mode 1, mode 2, or mode 3 fracture. So mode 1, you have this like discontinuity across the cracks. Some deformation field, like the green boundary in the metals, right? You have those slip bands, right? And you have some green boundary. So across the green boundary, sometimes you may not have the jump for the displacement, but you may still have the jump for the strain fields. So if you still use the conventional DSM method across the green boundary, you also have problems. This is the green boundary example that's in the magnesium alloys. So both in the fracture and in the metal, also in other fields, this discontinuity is very important problem. Like we want to address this issue. So today, based on this like a background and the current challenges, so I will review what's the current methods we want to improve, like to solve the complex geometry and to solve the discontinuities. And then I will introduce our new method. We call it the spatial temporally adapted quadtree mesh de-icing method. So before I introduce current methods, right? So basically all the de-icing methods, they can be cast into two categories. It's called the local method and the global method. So local method is you can divide the entire image domain into multiple local subsets. So you can track the motion of each subset locally and independently. So because they are tracked independently, so this method is called the local method. They can also be solved in parallel. So global method is differently. Usually we represent the domain using some finite element mesh, and we track all the nodes simultaneously. So because all the nodes they are tracked together, so that's called the global method. So about the complex geometry and about the discontinuity, both the local method and the global method, they have been improved to solve the issue. So for example, in the global method, right? So if you have the complex geometry or if you have discontinuity, so first of all, you can arrange your like location for the nodal points to follow the shape of the sample geometry, right? And if there's a discontinuity, so I will introduce you like two current methods of how they solve the problem. So if the discontinuity is very simple geometry, like the problem is very simple, and the analytical solution is known, so you can solve the problem. So for example, so this is the 3-point bending, and there's some like pre-cut notch there. So this is the fracture problem. There's some crack there. So there's crack. So you can see them images, but it's just not that obvious in the eye. But there's crack there. So if you use the conventional global method, you don't do nothing improvement, right? So you will track the deformation field, but near the crack, it will be smeared because it should have the like a sharp jump, but the deformation field they have been smoothed. So if you know, okay, I know the analytical solution of this fracture problem, right? Or I know this deformation field. There may be some like a parameter that's unknown, but you can fit those parameters. You see, I can track this X and Y deformation field, use these analytical solutions, and they are much like more accurate than the previous the global de-icing method, right? So this problem, you can solve this problem, but it only works well for very simple scenarios. Like you know they're the analytical solution, you know their form, right? But the more generally is the there can be quite a complex geometry or situation. You don't know the analytical solution, right? So for the global method, you can still improve to track those problems. So for example, you have some crack here, you have some mesh. So this is the finite element mesh, also your DIC mesh. And there's the crack here. So you see there are some of those elements, they had been, they have the interaction with this crack. So you can use the global DIC method. You can write the full field deformation field based on this global finite element basis function. But you need to extend those elements that they have the interaction with these cracks. So it's a very similar idea with the extended finite element method. You need to extend these basis functions. So for example, if you have the crack that had the discontinuous elements, right, you need to extend the basis function with the Heaviside functions. If you have the crack tip, right, you can also extend the base function, use the singular shape function for the crack tip. And you can solve this problem globally and track all the efficiencies. You can plug this into the image tracking optimization problem. So you can still solve the deformation field, along the crack. So yes, it works very well. But this problem is that you need to know, okay, where the crack it is, right? And you need to know, okay, which elements and which nodal points I needed to extend their basis functions. But the benefit is that this technique, it works for general case, for arbitrary geometry, right? So there's still lots of the pros to this technique. So all this is based on the global method, right? If you know their analytic solution, you can feed some parameters. If you don't know, you can just extend their elements. So this for the global. So for the local method, right? There's also the similar technique called the subset splitting strategy. Some people also call it the Heaviside DIC method. So the idea is very simple. If you have the crack here, right? This is the image. You have some crack here. So across this crack, there can be some discontinuity. So this is one of those subsets. So this is the one subset. Each square, that's the DIC local subset. The entire this red domain, that's the like a region of interest for the DIC problem. And for each local subset, because it's images, so you have so many pixels there, and there's the crack line that's in this subset. So the idea for the subset splitting is to split this subset. So you see, there's my centroid of my subset. So I can cut this element based on the crack line. And I only keep the part of this subset that's on the same side with my centroid point. And I discard the other minor part. And I only use the part of this subset track its deformation. Again, you can also remesh this like a mesh, right? Based on the centroid, you can put them just exactly along the crack line, right? Yeah. So it's still very good. It's quite useful. I can show you some example. So this is some crack here. Again, because this deformation can be very small. It can be less than 1 pixel. So there is the crack there, but it's just very hard to detect the crack by to use your eyes. You need to use the image tracking method. So in this paper, they tried both the large deformation, so the crack opening, the 5 pixels. They also tried a smaller deformation, the crack tip is the 1 pixel. So if you use the conventional method, so again, those subsets, they cross the crack, they may have problems. They may smear the crack tip. You see all this deformation, they have been smeared. If you use this like a subset splitting local method, right? So all the subsets near this crack line, they will be cut automatically. So, and you only always use the same part of the subset to track the deformation of the same subset centroid. So you can very nicely solve the problem and even cross the crack. You can solve this deformation field very nice. It's very sharp jump here. So it works very well. Again, for this local method, because you do lots of those cut those subsets across the crack, you need to like manually find, okay, which subsets I need to cut and how I cut them and which part of those information they can be used or they can be discarded. You need to detect all this manually. So from here, you can see for the complex geometries and for the discontinuities. So both the local method and the global method, they have been improved. So global method, you can either solve the analytical solution, or you can either extend the basis function, right? You can solve the problem. Local method, you can split your subsets, and you can track the local subsets, DIC subsets. They work well because I show you some example. You can track those very sharp jumps. You can also track the complex geometries, but they need a lot of those manual work. So again, in the global, you need to find, okay, which elements, which basic function I need to extend. Locally, you need to find how I cut the subsets, right? So what I want to do is, can we do this like automatically and more efficiently? So you may know the solution because that's the title for this talk. So we have the new method called spatial temporally adaptive quadtree DIC method. So we use the image mask files, and we to apply the adaptive quadtree mesh, and we solve this problem automatically. So I will introduce you the new method today. So imagine you have the image here, right? Because it had a complex geometry, there are 4 of those circular holes there. That's the background color. So only those like random pattern, that's the specimen. All the other color, that's the background. So there's nothing there. So first of all, this method uses the image mask files. It's because the image mask files assisted, but this is automatic method. So first, we need to generate this binary mask file. There are many ways you can generate this mask file. You can use the Fiji. You can just manually select the area, that's the sample area, right? Or you can use some intensity threshold method to do the image post-processing. You can use some machine learning based or like a neural network method. You can do the mask file automatically. But with this mask file, it's a binary mask file. So all the sample area, that's the 1. All the background, that's 0. So you can automatically generate a quadtree mesh. So the mesh, that's to follow the shape and the geometry of the specimen. So there are a few like benefits for this mesh. So first of all the nodal points, they are at the integer pixels because this is a quadtree, and each element it's a square shape, right? So if you choose the size of the square to be the power of 2, you can make all the nodal points there at the integer pixels. And if there's some like an area of the specimen, you have the high curvature or near the boundary or complex geometry, you will have more like a nodal points there. And also quadtree mesh is quite general. You can work this for arbitrary geometries. So here the one example is you see this is the same region for the DIC problem, and I can generate this quadtree. So near this circular hole area, they have been automatically refined, right? And this is how the refined mesh looks like. So each of these nodal points, that's the control point for my DIC problem. So this is the we use this mask file. First of all, we can generate this quadtree mesh automatically. The second is with this quadtree mesh, right? So for each like a nodal point, imagine I also have the subset around the nodal point. The second thing is that I can also do the subset splitting automatically. So imagine this is the blue box, that's the DIC problem. And the centroid for this blue box, that's the nodal point for the quadtree mesh. So for this subset, there's only the part of this subset, that's the sample area. And the other part, that's the background. So I can cut this subset automatically because I have the image mask files. For each of those pixel, right, I can only keep those pixels that's simply connected with the centroid point. And for the other points, that's the because the background that in the binary mask file, that's 0. So for all those pixels, I will just discard those. So I can only use those pixel information, simply connected on the same side with the centroid point for each subset. So this means that I can do this subset splitting automatically. I only keep the part of this subset. I do this for each of these nodal points. Here, just one example for just one subset here, but actually there are lots of subsets you can imagine. So once I solve this problem, right, as for each nodal point, right, I solve the deformation field. I do the subset splitting automatically. So here there's some like a geometry, you have some crack here. So there's the region 1 and region 2. So I also use this mask file to the interpolation. Because once you solve this problem, right, you solve the displacement field. Next, you may also want to compute the stream fields, right? So stream fields, that's some spatial derivatives. So here, so I use the method called the radial basis function. So basically, I have so many control points here. I want to compute the gradients of the displacement. So that's the stream fields. So I always choose the points, like all the data points, they are simply connected and they are on the same side of the crack. And I compute their gradients. The benefits of this is if you don't use this mask file to help you choose the where the data points they have be connected, you may choose the area like the entire circle. You include the data points from the both sides of the crack, and if you compute the gradients for these data points, oh, that would be very messy because that's not a true gradients, for each side of the crack, right? So now, like this string calculation can be improved. Use the mask file to indicate like how you choose the data points and compute the derivatives. So this is how I use the mask files. So similarly for the complex geometry near the boundary, I only choose the data points right on within this this region for this circle. For the crack, I choose these data points to compute the string. So here are some examples. So first of all, is some synthetic examples. So this is the uniaxial tension of the plate, and there is a circular hole here. Because this problem is synthetic. Synthetic means I have the reference image. I just apply some known deformation field to deform the image, use some MATLAB code. So I can generate some deformed images. So these are called the synthetic deformed images. And I can apply the DSM method. So this is the exact solution for the X displacement field. So I tried a conventional uniform mesh, the coarse mesh, and also I tried the fine uniform mesh. I also tried this adaptive mesh. I also, because I know the exact deformation fields, so I can quantitatively to compute their errors. So the coarse mesh, so you see near the like a circular hole, the error can be quite large because all these elements, if they across this hole, those elements, they have the like a very bad accuracy. So for the fine mesh is much better. The boundary is still the problem. Our new method is better because you can handle this subsets near the circular hole. You can do the subset splitting automatically. And also it's like a much more efficient because the total number for these data points is much less than the like a very fine mesh. Another example, that's the discontinuity. So here just some, so the specimen is rectangular. So I only shift the bottom part of this specimen for the rigid translation vector. So exact deformation field is 0 on the top and 5.5 on the bottom. So it's to the right. So the U is the 5.5 pixel and in the uniform deformation for the bottom part. So if I try the uniform mesh, right, you can see all the subsets, if they near this crack, right, they have been smeared. So you see, they should have the sharp jump, but they have been smeared. So if we try our new method, so all the data points near this crack, they will be like spatially automatically refined. And also you can handle this discontinuity accurately and efficiently. So this is a synthetic example. We also tried some like real experiments. So here the first is the real experiment for the complex geometry. So this is the same reference image, and we apply the mask file. We do the uniaxial tension for these hyperelastic foam materials. So we can quantitatively track their deformation fields. You see how the like a quadtree mesh, they have been deformed under this soft deformation fields. And we also solve the discontinuity problem. So this is a mode 1 fracture problem. And we can track their deformation field, and we can calculate their stream fields. So I also want to highlight the all these like adaptive quadtree mesh, right? They can be further refined or they can be adaptively modified. So for example, I start from current DIC mesh, right? The thing is I borrowed ideas from the adaptive mesh find element method. So I start from the image correlation, the correlation functional. I start from there. So I apply this adaptively technique. So I derive the error estimate for each elements. So I can find, okay, where elements, they have large of those like errors, right? So I can further refine those elements. So, and I can redo everything iteratively, right? So all the mesh, they can be further modified or changes based on this error estimate. So for example, this is the experiments from the Professor Rosakis and Dr. Vito Rubino. They do the earthquake, in-lab earthquake. So they do some plate here, right? They use these experiments to mimic what's the real happening for the earthquake. So actually, this is also the mode 2 fracture, but at very high spin rates. So they use the 2 million frames per second. You can track those image frames, right? And they're the crack in the center. So you can further refine the adaptive mesh based on the all error estimates. Again, here's some comparison for the new method with the conventional method. So if you try the uniform mesh method, right? So you see all the subsets near the crack, they have been smeared. So way to solve this problem carefully because he always solve the only top part or only the bottom part. So that's why you like his result, you can see the sharp jump here because you solve them independently. So our method is we apply the adaptive quadtree and we apply the subset splitting, and we can also solve this mode 2 fracture problem like quantitatively and accurately. Actually, there's a movie because there's real experiments. So you can see there the X displacement. There's some like a shockwave propagating. So the first row is the same with the second row. The first row is only to overlay with the original images. And the third row, that's the Vito's results because he solved the top part and the bottom part independently. So that's why he can also monitor those like sharp jumps. Yeah, our method is accurately compared with the Vito's method. Our method is accurate, and also because we use the adaptive quadtree mesh, we are also more efficient. So my talk is a little bit shorter today because I really want to introduce this new idea for the DIC that's been widely used, right? But for the complex geometry and for the discontinuity, data still like a significant challenges nowadays. And here we introduce a new idea. We use this adaptive quadtree mesh, and we can solve these problems efficiently and accurately. And I want to thank my collaborators, like owner, our sponsor, Dr. Tim Bentley, postdoc advisor, Professor Christian Frank, my collaborator, Dr. Vito Rubino, Professor Wenxiao Pan from Wisconsin Medicine, and other collaborators. So there are some other topics I'm not covered today. So for example, besides the 2D, right, we can also use a similar technique. We can track the 3D volumetric images, right? Also, there can be the complex geometry and the discounted there. And also some problems, particle tracking, they may be better than this subset method, right? So another one is we also apply this method in the laser-induced cavitation. So we can track like a very large deformation. So here the strain can be like 1,000%, like very large deformation. And there's bubble wall here, and also the complex geometry. So that's all I have today. Thank you.
Thank you, Jin, for that very nice talk. I'm sure there's questions. Is there someone who would like to get started with questions?
Yeah, I had a question. Thank you, Jin, for this talk. So my question is, how are you comparing your new digital image correlation results that you created with the stack method with other softwares and other DIC methods already available? Are you just visually comparing them, or do you have like a mathematical or like a data-driven way to compare your results between the two methods?
Yeah, that's a good question. So I want to give two comments for your question. So the first of all is so for the quantitative comparison. So one thing is that you can always do the synthetic examples because you know the exact solution in these synthetic examples, right? So you can quantitatively to compute the error. So the one thing. So the second thing is in the we call the IDIX community is the International Digital Image Correlation Society. So we have the DIC challenge and the DVC challenge problems. So there are the more than 10 data sets are available. So we also try to compare like, our new method to solve problems there. Yeah.
Okay.
So it's not only just to show you cool videos because you can quantitatively to compute these errors by the method.
So did you do all of them quantitatively to compare, or some quantitatively or some visually?
Oh, so for the synthetic example, you can always do the quantitative comparison, like all these error that's quantitative results.
Mm-hmm.
For the DIC challenge, I haven't do all the 14 one because all the DIC challenge they don't have the complex geometry. They only have the regular shape, rectangular shape, and our regular shape, right? The codes also compared with the other codes. So we have the paper published 2022 this year in January. So there's like more than 10 codes, like all the most popular commercial codes and academic codes, they are there. Yeah, I can send the link to you later. So there's also the new challenge just announced in this summer to try all the DIC codes for the discontinuity, like a crack or like a complex geometry. So this is still like this is still on the way.
Okay, all right, thank you. I might send you an email after this.
Sure, thanks.
I see that Callan has her hand up. Or hand.
Yeah, I think Emma does too, though. Emma, do you want to go first?
No, go for it.
Okay. Well, hi, Jen. It's really nice to meet you. I've heard a lot about you, and this is really important work for biomechanics community as somebody that tries to do everything full field, and it's really hard to do with biological samples sometimes. So I'm really intrigued by a lot of the things that you're doing here. I guess I have a lot of questions, but the most pressing is on your quadtree meshing, if I'm using the right terminology there. So you're getting these smaller and smaller subsets to deal with these odd shapes, right? Really important. But with biological samples, a lot of times, we don't have a lot of control over the size of our speckle features. We're trying to use all sorts of different things to get some kind of, texture to track. And that there's not as much control as you have with, say, black and white paint on a metal specimen. So how does it deal with, variations in speckle feature size, I guess, as you get these smaller and smaller subsets, is that a concern? And like, what can we do about that?
Oh, that's a good question. So kind of let me go to the one of the page and I can answer some of my comments. Yeah. So first of all, I want to comment is so all the nodal points, they have been specially refined, right? But each nodal point, there's a subset around the nodal point. So which means even like they have been refined like near the high curvature areas, right? They have smaller set for the elements, but behind each nodal point, there's still the some size for the subset there.
So is it like, maybe I was like misunderstanding, are you kind of tracking some of the points around the boundaries in multiple subsets? Like you're drawing
So
subsets at these nodal points. Am I understanding that?
So for example, if you have crack here, right, near the boundary, right? So
Yeah.
I'm not just tracking this very small refined element. I'm not do this. I'm still track some area for the subset. So the only thing that this subset had been cut.
Oh, okay. I understand. Okay.
So
I was
like
wrong twice. Got it.
yeah, this is very good question, because here there are two parameters. So one is what's the spacing between the neighboring subsets. The other one is what's the size for each subset. So here the spacing between the neighboring elements, they are smaller if mesh had been refined, right? But each element size, they at least have the 50% area. That's you always have the speckle patterns.
Okay, I understand now.
Yeah, that's a good question.
My question does still stand a little bit about subset size and like how, I guess, how much you know about using this on super extensible elastomeric materials and with different feature sizes. But we can talk offline.
That's good comment. So there are two quick comments. First of all, is there's the error. I can go to this page. Yeah. So you always have you can do the quantitatively to measure the noise floor before you do the DIC, because it depends on like your experimental noise, the sigma, that's the noise for the experiments. It also depends on the is square root of the summation of the image grayscale value gradients. So if you already have some reference image, right, you can compute those image grayscale value gradients. You can compute the sum of those grayscale value gradients. You can already do some calculation for the noise floor before you do the DIC analysis. So imagine you have the same sigma for your experiments, right? Because if you choose a different element size, if you choose a different subset size, the bottom part, right? Because the sigma here, you have different number, so you can compute your sigma u like based on like, do you need more pixel gradients there or do you need less there?
All right, cool. Thank you, Jin. Great talk.
Thanks.
Okay, Emma changed her mind, which I think is out of respect for others who want to.
My question is ended, so I'll just ask at the end.
Okay. Otman, do you want to go next?
Yeah. Hi, Jin.
Hey, Otman.
Thanks a lot for the great talk, for sharing this with us. Very well explained. So maybe I missed this, but I was just kind of wondering, since you're starting off with with this binary mask and then you're discretizing that, how well do you handle new discontinuities? So for example, when you're tracking a crack, you have some pre-existing discontinuity and you're sort of evolving from that. But let's say in this image that you have up here, on the left side, you basically have a new void, a new hole that appears under some large deformation, right? So maybe in a way it's related to the cavitation work, right? So let's say under like some large deformation, you get cavitation. So how well do you are you able to adapt to something like that?
Yeah, that's a good question. So for the tracking, so there are two tracking modes. It's based on the Lagrangian or Euler ring. So Lagrangian one is you already know there's some pre-existing crack there, right? So you can just generate one mask file, use the reference image. And for your mentioned either if you have some new crack there, right? So I will have the code either you need to do the mask file for each frame.
Okay.
And we use the Euler ring tracking mode, so we can handle this problem.
Okay.
And there's still something so what if you don't you cannot generate those binary mask files, right? Like your discontinuity is just so small. It is there, but it's so small. You cannot have those like a binary mask file before the tracking. So there is something I didn't include today because I have one comment here, the other mesh, they can be further refined, right? So you can always to compute those like error estimates, you can further refine the mesh. So even of some of those discontinuity, they are so small, you cannot use some Fiji or some other software to measure those. You can still, based on these error estimates, you can still update and refine the mesh.
Okay, that makes sense.
Thanks.
I'll have to read. I need to read your paper. Should have read it.
Oh, we can talk more later.
Yeah. Thanks, Jen.
That was the question that I would have asked, but I have one other. Suraf, do you want to go next?
Yeah, thank you. Hello, Professor Yan. Can you hear me?
Yes.
Yeah, great talk. Thank you. So I had a question. You just mentioned, you were mentioning that you use Eulerian-based tracking, right? I mean, so because that might be suitable for small deformation because if the deformation is large, we are assuming that there's a projection, right? And the image-based tracking from one image to the next temporal image, there's actually we're projecting the deformation. So how that will and when that will fail, or would that be a concern? I mean, because of that Eulerian approximation.
So that's a good question. So first of all, for the Eulerian, we generated the quadtree mesh for each frame. So for other deformed frame, we also have the mask file. The good thing of this is because if you only have one quadtree mesh, right? So the topology of the mesh will be quite different if there's a new crack there, right? So that's why for each frame, for each deformed frame, we also have the binary mask file and we have the quadtree mesh, right? For the second comment is because the images, they can be large, right? So maybe you heard either the cumulative mode for the tracking and also the incremental mode of the tracking, right? So for the cumulative mode, you are always comparing with the very beginning reference image. And for the incremental mode, you are always comparing a subsequent 2 frames and then eventually do some interpolation. Right. So if your deformation strain usually is less than 30%, this number is just some empirical number, right? So usually the cumulative mode it works well. But if your deformation is very large, over 30%, right? So I would recommend you the incremental mode. So all the video I showed for the cavitation, that's the 1,000 more than 1,000% strain, we use the incremental mode. So this is the. Yeah. So here I do 2 things. First of all, for each deformed frame, I have the quadtree mesh. Secondly, I use the incremental mode.
Okay, yeah, that makes sense. Also, just another question. So, you were using that adaptive meshing, and you were just refining the meshes inside near the discontinuities, right? I mean, can that be? Can we apply any deformed window there as well, and how much computationally extensive that would be? Is that possible, easier to do? My question is that. Yeah.
So what do you mean deformed window?
In addition to that adaptive meshing, does deforming the window based on to resolve the gradients of the displacement, would that help that much?
Yeah, that's a good point. That's correct, because also Kala have the similar comment related with your question. So because the different area, because they may have different speckle pattern, right? They may have different grayscale value gradients, right? So if you want to have the same noise floor for all the subsets, you may need a different window, right? So even for the same experimental noise, if you have different here or there, you have different distortion, right? Different strain. You may also need a different size of the window, right? Yeah. So all these you can follow those analysis of this error. You can modify the code easily, because this is the more details how do we keep improving the accuracy.
Yeah. Thank you very much for your answer. You did a great job. Yeah.
Thanks for the question. That's a really good question.
Jingji, do you want to go next?
Hi, Jing. How are you?
Hi, Jingji. It's great.
Yeah, it's very nice seeing you here, and I really enjoyed your talk. I just have a couple of quick maybe clarification questions. I guess there was a slide you were showing the strain field when you're having laser-induced cavitation. I guess my question is I hope I understand it correctly. Is it does the source of cavitation really matter for the method over here? For instance, if we have ultrasonic cavitation, you can still use it for the DIC to calculate the string field, right? It doesn't really matter whether it's being laser activated or some other source being activated here.
It doesn't matter. So as long as you have the very nice image qualities.
Okay, I see. One other question is more like general, is regarding like, I think it's more like on the type of the sample case that we're dealing with, like biological related samples, and some of them are not exactly, solid, or some of them like semi-transparent, or even have like a lot of transparency. I guess maybe like just in general, based on experiences, like I guess like how does like that transparency, or like some sort of like a percentile of the transparency gonna, let's say, affect these results, or like having how much, like in terms of like limitations or uncertainties we should be like be careful about on that front?
Oh, that's a good question. Like your question is related with the actually the how we paint those speckle patterns.
Yeah, right.
Yeah. So so for the 2D DIC and also the Stewart DIC, because you only track the surface of the specimen. So usually the transparency, I don't think there's a problem there, because you only track only the top surface, or most outside the surface.
Okay.
Yeah. Also there, I can send you there the paper in the like 2014 or 2016. There is a very nice review paper, like to introduce how to paint a pattern for the hard tissue and the soft tissues. There are very nice review paper there. Yes. So for the like volumetric tracking, because sometimes you want to track like a very deep, right? If you use the confocal, right? So like for those, like transparency also problem, because you scan those images, volumetric images layer by layer. So if you have the transparency problem, you may lose some like resolution there.
Okay. Yeah, I understand. Yeah, I'll take a further look at the papers you mentioned. Thank
Sure,
you very
thank you.
much.
Yeah.
Is there another question in the audience? Can you help me understand, how do you deal with the problem of collapsing elements, if that is something that you encounter? So if you use a quadrilateral mesh, do you ever have inversion of the Jacobian because of collapsing elements, or is that where you just keep on refining, especially at boundaries? Is that an issue?
Excuse me. Oh, that's a good question. So first of all, so my understanding for the collapse is if the element goes to a very small size, right? So even less than 1 pixel, right? That is some collapse, because the images, right, we cannot reach some pixel less than 1 pixel, right? Yeah, I would say those collapse. So if you always use the Lagrangian mesh, so you only use just a fixed mesh based on the first reference image. So for those collapse problem, if you use the quadtree mesh and track each nodal point, right? For that nodal point, you have just a bad point there. So you have the locally bad point. So that's fine, because even it's a locally bad point, but eventually, remember, we do those interpolations. I can show you the interpolations. So even you have some local bad points, right? So because eventually we do the interpolation, and this we use the radial-based function, we use the spline interpolation. So you can still get some good results. And the second thing is if you are not using Lagrangian tracking, use the Euler tracking. So now all your mesh are generated for each deformed image. So even there's some like a locally collapsed, right? But because all your mesh now is generated based on the deformed mask file. So there's still no problem for those elements.
Okay. All right, I think, Emma, it's time for your open-ended question.
Well, I basically, I first of all wanted to say that was a fantastic talk, and I've been following your work for several years, so it's really nice to finally.
Thanks, Emma.
Yeah. And I think that my very, very open-ended question, there's kind of two parts to it. The first one, I'll put a link in a chat. I work on collecting some data sets that are relevant to mechanics. And someone suggested to me to include the cardiac motion analysis challenge data set on this list. And it's just like a link to the data set. I would love to also add some DIC relevant data sets to this list. And maybe that's something we could follow up on in the future. But I would love to hear what you think about using machine learning for digital image correlation. It's not something that I'm working on or necessarily plan to work on, but as such an expert on the area, I'd love to hear what you think the I'd love to hear what you think about it.
Oh, that's a good question. So in my opinion, machine learning, the combination about machine learning and digital image correlation, they have three aspects. I think the first one is because the digital image correlation is based on some image tracking algorithms, right? So there are already like many available machine learning codes or algorithms, right? They do the image tracking, so they can be applied directly. Also here you see I use the mask files, right? So in the machine learning field, there are also the mask file method, right? Those can be directly applied. So all these, I think the machine learning can be used for the image tracking algorithms, both 2D and 3D. So second one is we get the DIC results, but eventually we need to use these results for the materials characterization. So how to you have those data points, right? Like lots of data there, but how to do the material characterization more efficiently and faster, right? I think this need help use the machine learning method. And also because the DIC and the DVC, we generate the data because we can have the data for the heterogeneous definition field. So we can generate quite a fruitful data sets with much fewer experimental test numbers, right? So I think there's some bridge there can combine the DIC with the machine learning characterizations. And the third thing is so recently is how to bridge the gap between the experiments and the numerical simulations, some computer mechanics, right? So because the materials calculation, you may still use some model, right? But what if you don't have model? Because I know at least the Professor Michael Ortiz, other professor, they are leading this area. So skip the a modeling part, just to bridge the real experiments with the new computer mechanics. Lots of those data-driven methods. I think there's also lots of the opportunities there too.
Yeah, thank you so much.
That's a good question, Emma, because I'm still, because this field is still developing. Just my personal opinion.
That's why I had to ask. Yeah, maybe I'll ask you again next year and see if you say something different.
Yeah, we should chat more. Yeah.
Yeah, that would be awesome. It's great to meet you.
All right. I think this was a really nice discussion. So clearly a topic of interest to a lot of people in our field. So thank you again for joining and sharing your work. And I hope you join or follow our journal club in the future as well.
Thank you for coming.
Yeah.